Hello, good morning and good afternoon for some of you. I'd like to welcome you to this webinar organized by VentilAQUA and entitled Advanced Technologies for Textile Wastewater Treatment. For those who don't know me, my name is Francisco Oliveira and I am the sales manager of VentilAQUA, and today I'll be your host and moderator of the conversations and discussions that we will have about wastewater treatment. In the next hour, approximately 1 hour and a half, we will be discussing about effluent treatment in the textile industry. We all know that the textile industry is one of the most wastewater intensive industries, if not the most one worldwide. And that's why it's always important to discuss these matters, know to the challenges placed to this sector, and the advance of the available technologies to deal with these complex wastewaters. So we will be discussing all these, which is something that for sure concerns us all. And to do that, we will be counting with the presence and collaboration of our speakers. First, we will have Wölfgang Höhn, Senior Engineer and Technical Consultant for the textile industry. He's coming from Germany and he is well known worldwide in the sector. He has been working many years focusing the environmental aspects of textile industry. He will give us an insight of the worldwide situation of the sector and of effluent management in the textile industry, which is always important to evaluate and remind and discuss about. And after Wölfgang later, we will be counting on Carlos Oliveira. Carlos is the CEO of VentilAQUA. He will be making a brief presentation on new technologies for textile wastewater treatment, many of them developed by our company, by VentilAQUA, along the recent years, which delivers a new approach to many of the new challenges placed to the sector. Just to give you an idea on we will be running the webinar, we will have a Q&A moment for you to place questions and doubts that you want to be answered. But we'll do it only after the finishing of both the presentations. That doesn't mean you can only place your questions at the end. You can do it at any moment. We will have a queue line, let's say, of questions, and we will place them available and publish it by the end for the Q&A phase. So feel free to ask all the questions that you want, that we will try to answer them. So once again, I'd like to thank you all for being here and for taking part of this webinar. We are very honored with your presence, with such an eclectic and diverse group of people, coming from so many technical fields and so many geographies. For you to have an idea, we have now more than 150 participants connected to us now, coming from 5 continents and more than 25 countries. Naturally, we are very pleased and honored with that. This is a reflex on how these topics mean so much for so many people worldwide. So with no further delay, we will start this webinar. And as I explained before, we will start by Wölfgang Höhn with this lecture. So Wölfgang, be my guest.
Many thanks, Francisco, for the kind introduction. Ladies and gentlemen, welcome. This is Wölfgang Höhn from Höhn Textile Engineering. I am an independent consultant and freelancer for VentilAQUA with much textile chemical expertise. And I will support them for the textile industry related wastewater projects worldwide. Therefore, they have invited me to share this webinar and to give you a lecture about effluent treatment in the textile industry, as you can see on the slide. This presentation is providing for a rather comprehensive and up-to-date survey about this special topic. Due to lack of time, my lecture will last approximately 30 minutes, by the way. I will avoid to go too deep into all the details. But of course, this can be made separately once you will approach me with particular problems and questions in the future. Now let's start with the presentation. Ladies and gentlemen, the textile industry is one of the most wastewater intense industries, if not the most wastewater relevant one at all worldwide, as Francisco told you already. Therefore, there is hardly a sector known of industry which needs more to consider and to take care for providing measures of sustainability in terms of the aquatic environment. Coming to the term sustainability, which is nowadays more important than ever and will be in the future getting even more important everywhere. Ladies and gentlemen, sustainability of wastewater management in the textile industry can be confidentially achieved only by a well-organized company concept, comprising permanently optimized methods of production, integrated wastewater minimization, effluent clearing, and wastewater recycling and reuse. This is nowadays a crucial challenge for the holistic environmental management of every textile finishing company, the importance of which is permanently increasing over the years. What will you learn today from me? What can you listen to? First, about the effluent minimization within the production. And second, and this will be the main part of my lecture, about the effluent minimization after the textile production. Just to give you a survey about the contents of my presentation, I will start with a situation report about the textile industry effluent. Then I will talk about the effluent impacts by the textile industry, the most relevant effluent impacts by them. Then I will make a fiber focus on the impact. I will talk about the impact by cellulosic protein and synthetic fibers. And I will focus more on the make-up related impact. What is the pollution? What is the contamination of effluent in case of yarn, knit good, and woven fabric? The next chapter will be the effluent regulations and the guidelines for the textile industry. Mainly the global and municipal governmental effluent regulations, but a part of them, there are also guidelines more and more of private organizations. And therefore, I will show you a slide comparing the governmental regulations with those of the private organizations, which are really quite different. Finally, last but not least, I will come to the main part, to the core part of my presentation, which will be the effluent management in the textile industry. I will give you a survey of processes for effluent cleaning. I will tell you types of processes for effluent recycling, reuse, more and more important. I will tell you about the so-called production integrated measures in order to reduce the textile effluent. And last but not least, as a conclusion, I will give you the ideal wastewater concept as a summary. What is the situation of the worldwide textile industry effluent? As already told you, the textile industry is the most effluent element industry segment worldwide, even prior to the chemical, to the food, and to the paper industry. The effluent costs amount currently in average 10% of the total textile company costs, and we have to differ between the effluent fees on the one hand and the effluent treatment costs on the other hand. We can face considerably continuously more restrictive effluent laws and more pressure by private regulations in terms of wastewater. This means that an efficient effluent management is getting more and more important, and permanently the price of textile is increasing due to that, unfortunately. But there are possibilities, and I will talk about them, how to avoid it. We have to differ between two different effluent discharge types. First, the direct discharge. The direct discharge means the discharge of the effluent, the cleaned one or the non-cleaned one, into the waters, that means the lake, the river. Approximately 5 to 10% of the textile companies so far are applying the direct discharge. The tendency of them, however, is increasing step by step. More relevant nowadays still is a so-called indirect discharge. It means the discharge of the effluent into the municipal wastewater pipe, which is flowing into the finally into the municipal wastewater plant. Still 90 to 95% of the companies are applying this kind of discharge of effluent. The tendency from, however, is decreasing step by step. What are the impacts onto the effluent by the textile industry? What are the contaminations of effluent? What are the pollutions of effluent? Differentiated by substrate. Here you find the most relevant effluent impacts by the textile industry, which are listed in order of decreasing importance. I would say color is the main issue. Color is the main issue, less because it's toxic. It's not toxic at all in the most cases, but from psychological point of view, from aesthetical point of view, it's the most critical thing for dye houses that the effluent is colored by the residual dyes, which are not fixed, and that the waters afterwards, the rivers, get colored. Second important, or maybe we can discuss about even first important, is a organic freight measured as COD, chemical oxidation demand, or as dissolved organic carbon, the organic freight, which is at the end a burden for the municipal wastewater plant, because the municipal wastewater plant must be able to remove all this organic freight due to a minimum value. Then we have to consider low bioeliminable, also named persistent, refractory, or recalcitrant substances, which are very difficult to be biologically cleaned and removed. Then, of course, there are aquatoxic substances also occurring in dye houses, inclusive heavy metal ions, particularly chrome-3, copper-3, and cobalt-3, which are not free usually, but bonded, complex bonded within the metal complex dyes, or the phthalocyanine copper dyes, the Turkish ones. Then we have a AOX contribution. AOX stands for organic bonded halogen or chlorine. These substances are also a problem for the aquatic environment. APO. Still nowadays, APO means alkyl phenol oxalates are not completely disappeared in the textile chain. But for instance, there are many countries still where wool is washed and by APO containing nonyl phenol oxalate containing surfactants, and also subsequently it's preparated by APO, emulsified preparations, and therefore still is a problem also occurring in those companies who are buying wool containing APO and washing it. Sulfur containing substances are always a problem, sulfide and sulfite, because they are toxic for the aquatic environment, and sulfate because it's concrete. It's corrosive for concrete of the effluent pipes significantly, at least with a concentration of higher than 0.5 gram per liter. We have got bioaccumulating substances. These are substances which are accumulating in the food chain due to their fat solubility. We have eutrophicating substances which are fertilizing the river, increasing the growth of algae. These substances are usually inorganic and organic bonded nitrogen and phosphor compounds. Extreme pH values in both directions, either in the alkaline direction or in the acidic direction, whereby I have to tell you that the aquatic organisms are more sensitive to acid than to alkaline pH value. Quite contrary to our skin, for instance, which is more resistant to acid. Then we have high electrolyte concentrations, particularly in cotton dye houses, where we apply a reactive dyeing, or mainly in case of reactive dyeing. And last but not least, we have cancerogen, mutagen, and reproduction toxic substances, CMR stuffs, which, however, are less an issue for effluent as they are an issue for the production itself or for the textiles where they can be found on. The COD value, the organic freight contribution by the textile industry, it's quite interesting to observe on this circle diagram where they come from mainly. What are the sources of COD? We can see here in this diagram that the main part, 50 to 60%, are not coming from the textile auxiliaries or textile chemicals, but they come from the gray material where you have sizes on, preparations on, and you have got fiber impurities on. Then we have pretreatment agents, which already have an extent of 15 to 20%. The auxiliaries for dyeing and finishing also amount to 15 to 20%. And the colorants, the dyes, of course, have the lowest COD contribution, but despite of they are the main issue because of their color itself. This is a problem of dyes, not the COD value. When I check now what are the specific impacts related to the individual fiber, which is dyed or which is finished in the textile company. In case of native cellulosic fibers, the main COD value is caused by the native fiber impurities. By the way, I don't consider their preparation on this slide yet. I will consider it on the second slide. Yes, native fiber impurities are causing a high COD value. Then the washing auxiliaries and sequestering agents mainly are contributing to COD value. You have a lot of salt in native cellulosic fiber dyeing, particularly in case of reactive dyeing. You have a high alkaline pH usually after reactive dyeing, after wet dyeing. You have much color, mainly resulting from the reactive dyes, which have only got a fixation degree of 70% plus minus, as you know, and also sulfur dyings, which have a very bad yield. And last but not least, we have also aquatoxic substances, which are the after fixing agents for the fastness improving based on quaternary polyammonium compounds, which however are by far not that toxic as monoquaternary products as they are used, for instance, in polyacrylonitrile dyeing as a retarder. In case of regenerated cellulosic fibers, viscose fibers or lyocell fibers, for instance, the impact is comparable to that of native cellulosic fibers, but without, of course, the native fiber impurities, and also you need less washing auxiliaries and sequestrants for their finishing and pretreatment. The protein fibers mainly contribute native fiber impurities like fats, waxes. They contribute washing and dyeing auxiliaries, increasing the COD value, and as you know, you are using usually metal complex dyes containing chrome and cobalt, which are a serious issue for the effluent and which are very severely restricted, even for indirect discharging companies. You have an acidic pH, a low pH, which I told you already is more critical than alkaline pH for effluent and absolutely needs to be neutralized prior to discharging. Polyamide fibers, quite similar to protein fibers, but of course without the fiber impurities. Polyester fibers, on the one hand, you have a contribution to COD by washing and dyeing auxiliaries. You have got an alkaline pH. Okay, you are dyeing at acidic pH, but at the end you make an alkaline reactive clearing process, which causing a strictly alkaline effluent. And you have also resulting from the reactive clearing process a much organic or inorganic bonded sulfur causing sulfide, sulfide, and sulfate. Polyacrylonitrile, a less important fiber nowadays, is contributing to the COD by washing and dyeing auxiliaries. It's contributing to an acidic pH, and of course, due to the retarders, it's also a little bit contributing to toxicity, but as you know, the retarders are by 95% fixing on the fiber. This means they are not relevant for the effluent itself. In case of fiber plants, of course, you have got the individual fiber impacts. Now, after considering the fibers themselves, now I consider the impact depending on the makeup of the textile. And now I consider the preparations. In case of yarn finishing, you have actually a lower amount of mineral oil-based and synthetic preparations, causing a quite low COD contribution. In case of knit goods, you have already got a higher amount of mineral oil-based and synthetic preparations, And in case of elastan blends, you have also got silicon present, causing a medium COD contribution. But last but not least, the woven fabrics, in this case, you have got the by far highest COD contribution, once due to the synthetic sizes and warp waxes, which have got at the same time a very bad bioeliminability. And you have got native sizes, starch and starch derivatives, which have got an even higher COD contribution compared with synthetic ones. But of course, their bioeliminability at least is better, too much better. Now I come to the effluent regulations and guidelines for the textile industry. In most countries, ladies and gentlemen, the legal basis for discharge of water, wastewater, is defined in a general wastewater law of government. For instance, in Germany, it's a Wasserhaushaltsgesetz, paragraph 7. This law is usually concretized for textile blends in a legal degree in case of direct discharges. In Germany, it's a famous Appendix 38, or by municipal statutes, kommunale Satzungen for indirect discharges. And these regulations are defining commandments, prohibitions, limit values for different wastewater parameters, ingredients, and the wastewater fees themselves. Of course, there are different regulations for direct and indirect discharges, and those for the direct discharges are, of course, by far more severe and restrictive. Worldwide, there is a tendency for these regulations to become step by step more severe and more restrictive. And you have to meet this development. A part of these governmental-based regulations, step by step, we face more regulations, or let's say guidelines, from private organizations. For instance, ZDHC, or Bluesign or GOTS, or major companies or retailers like Lieferung. They are defining their own rules and guidelines, which might differ from those of the government sometimes. And in this slide, I would like to show you the differences between the wastewater limits by legal regulations and those by private guidelines. On the left hand, the legal regulations in green color. Actually, they reflect a high expertise in wastewater management. In average, the regulations are less severe and much more feasible compared with the private regulations. You have got a clear differentiation between indirect and direct discharge. You have only the real relevant parameters being regulated, not the irrelevant ones. And mostly the limit values are higher to much higher compared with private guidelines. On the other hand, on the right hand in blue color, the private guidelines, they reflect usually a minor expertise in wastewater. I can charge it. In average, the guidelines are more severe and less feasible. Mostly, there is no clear differentiation between indirect and direct discharge, which is a big problem from my point of view. Often, much more parameters are regulated, even those which are not relevant at all, in my opinion. It's only my personal opinion. And often the limit values are lower to much lower compared with legal regulations. Sometimes, however, they are higher. And in case the limit values are higher and the customer is following the guidelines from the provider organizations, he will injure the legal regulations. This is also a problem. Now, last but not least, I come to the main part of my presentation. All the other things have been just the introduction to give you a impression of situation. The effluent management in the textile industry. Ladies and gentlemen, now we consider the effluent cleaning methods. If they are used just to clean the wastewater for discharging it into the effluent pipe or into the river, we are speaking from end of pipe processes. There is no use usually, no reuse. We have to differ between the state of art. First, we have some technologies which are old-fashioned but still applied and permitted. They are named technologies according to general accepted rules of technology. Then we have the best technologies for the time being, named state-of-art technologies. And then we have technologies which are already developed, but which are not broadly used. They are still in state of science. According to the principle of cleaning, we have to differ between compensation processes, substance separating processes, substance destructing processes, and combined processes. First, the compensation processes. Compensating means a neutralization and compensating of effluent in the buffer or neutralization basin and tank. At first, you will achieve by these compensating processes a quantitative hydraulic compensation, means you will achieve that you will have a constant, more or less constant volume flow of your effluent. On the other hand, there is a qualitative compensation. You compensate concentrations over the time that, for instance, the COD rate is constant more or less permanently. You have got a compensation of temperature. You will lower the temperature below 35 degrees, which is usually the limit value for a indirect discharge. You will compensate and neutralize the pH value, for instance, by flue gas or by separate acid. The pH value usually relevant for indirect discharge is between 6 and 9.5 pH. And also you have the problem in the effluent, particularly in the high in the warmer season, that there is occurring sulfide by anaerobic processes. You will smell it, and this is toxic, extremely toxic, and you have to detoxificate it. You have to remove the sulfide by oxidative measures, and the easiest one is a ventilation. This ventilation has to be strong enough in order to achieve no smell at all at the end. If not strong enough, then you have to add peroxide, hydrogen peroxide, for instance. These compensating processes are elementary and cheap cleaning steps against load peaks. They mean a minimum equipment for every indirect discharger, but they are no real cleaning equipments, apart of the matter of fact that there is a partial sedimentation of suspended particles. The next stage, and now I come to the real cleaning stages already, is are the substance separating and concentrating processes. First, we have to consider one of the most famous and most used process and technology, which is a coagulation, precipitation, also named flocculation, either by conventional inorganic coagulants like iron or aluminium salts, or by modern inorganic coagulants like bentonite, or by modern organic coagulants like polyquaternary ammonium compounds. This flocculation is a cheap process. It's universal. It is removing everything, not completely, but at a high extent. It is, however, only useful for indirect discharge, and the problem is that there is much sludge generated, which have to be removed separately. VentilAQUA is offering this system, by the way. The other higher advanced technology is the adsorption filtration technology. Of course, there is a coarse filtration on the one hand, which is able to remove by pebbles some particles. More interesting is the adsorption ion exchange technology for instance, by bentonite or by activated carbon. But most important and most common is a membrane filtration, like ultrafiltration, nanofiltration, reverse osmosis, electrodialysis. Probably you heard from already. An expensive method in terms of installation or investment, but it permits you even a direct discharge and even more recycling. Also here, VentilAQUA is offering systems. Other technologies of substance separation, like ion pair extraction, evaporation, and so on, are less important for the textile industry. Ladies and gentlemen, these separating processes have one disadvantage. Generally, they are not really removing the effluent load, the contamination. They are only shifting it from one environment compartment water through another environment compartment waste. But actually, they are not really destroying or eliminating this contamination. Quite contrary to the next stage, the substance destructive processes, which really more or less are removing the wastewater freight by mineralization or other methods and principles. First, the oxidative processes. Of course, everybody of you knows the aerobic biology applied in the municipal wastewater plants. Then we have got chemical oxidations by ozone application or by application of Fenton's reagents, which is iron 2 ions in hydrogen peroxide and at a strongly acidic pH value. And we have chemical oxidation processes with pressure using peroxide with pressure and catalysts. This technology is named wet oxidation. The aerobic biology permits a good COD reduction, but only a poor decolorization. And of course, substances which are persistent, which are recalcitrant, cannot be eliminated by. The chemical oxidation is only suited for decolorization and from cracking of persistent components. It's cracking those components which are persistent, and then afterwards it can be removed by aerobic biology. And we have the wet oxidation, which permits a total mineralization, however, which is not able to remove the inorganic contamination. Then we have reductive processes, the anaerobic biology, and chemical reduction processes using sulfur-based and sulfur-free reducing agents like sodium borohydride or iron 2 in alkaline medium. The anaerobic biology always is combined with aerobic biology. The anaerobic biology is cracking the resistant components, which now are accessible to an aerobic degradation. The reducing agents are only useful for decolorization and for removal of heavy metal ions, since reducing agents are able to transmit the ions like chrome, like cobalt, like copper into the solid, into the free iron, into the free metal, which is sedimenting. And last but not least, and this will be the main part of the subsequent lecture of Carlos, is there available a simultaneous oxidative and reductive process, an in situ combined process of 2 stages named electrocoagulation or electroflocculation. It combines oxidative, reactive, and flocculation and flotation processes. And even more, it's well modularly expandable, for instance, by a subsequent membrane filtration for wastewater recycling and reuse. We will hear more about that from VentilAQUA from Carlos later on. Okay, these have been the different technologies. I did not go too much in details. I could do so, but the time is missing, therefore I avoided. Of course, a combination of processes like compensating processes, substance extracting processes, substance separating processes as the last stage, named polish step, is the best way to clean water, even for higher demands as direct discharge or even for reuse. This is the best state of art. And although the electrocoagulation system I mentioned from VentilAQUA is following this scheme. This leads me now to the reuse, to the recycling of effluent. If you have only an end-of-pipe process, if you just clean for discharging your effluent into the municipal pipe or into the river, you are not saving costs. You're only meeting the legal limit values and demands. But if you reuse, if you recycle your water, then you have really a saving potential. And in this case, we are speaking from the so-called payback situation. And this is the importance. And the technologies I've mentioned before, particularly the combined process, for instance, the electroflocculation, is enabling you even to reuse to recycle the wastewater, saving money for fresh water. We have more or less 4 different types of recycling processes. We have the recycling of wastewater mix. We have the recycling of partial flow wastewater. We have a recycling type which not even needs any cleaning, which is a reuse of contaminated rinsing liquors as promoted by the company Thies, for instance. And we have a reuse of treating liquors by themselves. As you know it from sulfur dyeing, you can repeat the sulfur dyeing 5 to 10 times in the same bath. In this direction, or in this order, from the first to the last position, you have an increase of economy and efficiency. On the other hand, the flexibility is getting less and the expenditure you have to apply is getting higher. So you should check which of these recycling stages are suited in your company, whereby you should prefer the last one to the first one. These recycling technologies here in pink color, they are an intermediate position between the lowest economic end-of-pipe effluent clearing and the highest economic production integrated methods of reduction of wastewater. This, before you do something with your wastewater, before you clean it, before you recycle it, you should first check which methods you can apply in your production to reduce the wastewater freight. And now I come to this important point now, and I'm an expert in that. So if you need some support here for your individual company, I can help you. What are the production integrated measures of wastewater reduction? What can you do in your company, in your production, to reduce wastewater, to avoid any wastewater load, to minimize the costs of subsequent wastewater cleaning and recycling? First of all, you should consider new dyes, new auxiliaries, dyes with an optimized degree of fixation, for instance, as for instance bifunctional reactive dyes or reactive dyes which need less salt or less alkali or less temperature, which are available nowadays, and I know them and I could help you with that. And generally, the use of electrotoxicologically based dyes, auxiliaries and chemicals and recipes for the individual applications. Now an important second sentence, as far as no inherent technical and economical disadvantages are occurring. Of course, the operational safety of production must be ensured and the cost should not be increased by any alternatives. A part of the new dyes and auxiliaries, also there is worthy to consider new and improved finishing processes. There are some available nowadays which are very important, and I came across some during the last time. For instance, a plasma pretreatment without water offered by Crimp Italy. It's applicable, for instance, for cotton. You can bleach cotton with plasma without any water. You can achieve a superwash effect for wool, a removal of the scales by plasma without water. And you can prepare, you can improve the washing effect, maybe on polyester, by pretreating it with plasma. And you can save, in case of inkjet printing, for instance, you can save the preparation of inkjet printing just doing it by the plasma treatment without water. Then we have pretreatment for better dye fixation, for instance, cartonization processes. The dyeing at liquor ratio, at low liquor ratio, is something which should be aimed at. You can save water, much water, but on the other hand, you must be aware of higher concentration of the freight in this case. You can combine preparation and dyeing processes or preparation, dyeing and finishing processes in one bath. Then there are available already according to state of art, no longer according to state of science, dyeing systems completely free of water. The carbon dioxide fabric dyeing, which has already started 15 years ago, is nowadays commercially available by Dyeco Netherlands. Or the digital yarn dyeing, a yarn dyeing system on the continuous running thread, which is quite similar to inkjet printing. This is offered by Twine Israel. These technologies I came across recently, and it's very interesting to read of them. I think the most of you might not know them. Okay, there is also the way of an optimized after soaping and rinsing process, saving a lot of water, and substitution of inecological processes generally. So maybe Carlos, the subsequent speaker, can help you a lot in wastewater clearing, but I can help you a lot in addition, and mainly in terms of these production integrated methods in order to optimize your production. I'm also cooperating with dyeing auxiliary companies providing sustainable auxiliaries, and I can help you to optimize your systems. It's now to the last slide I would like to show you. It reveals the ideal wastewater concept. It's nothing else but a summary of everything I have told you so far. You should do in your company, you should check in your company how I can improve my production in order to reduce wastewater. You should optimize your production integrated methods, plant specifically, of course. Then you should check if you can do some recycling in your company to save water. And if you have exhausted or exploited already these measures, then you should check at the end how you could optimize your end of pipe processes, your pure cleaning processes at the end. These technologies here, of course, in an optimized manner, should be combined by two organizational measures. On the one hand, you should prefer the partial flow treatment of water compared with a mixed water treatment. The partial flow treatment is always more efficient, effective, and so on. And also you should consider a so-called holistic concept. This means you should consider the complete company stream of stuff, of water, of energy. You should also include, for instance, the heat recovery in your wastewater concept. If you consider all of that, you will achieve minimum costs on the one hand and maximum saving of resources on the other hand. Finally, leading to an ecologically and economically optimized wastewater concept with minimized costs, permitting a payback situation, and with low to zero effluent. Ladies and gentlemen, this was my presentation. You have the chance to write questions, and after the second lecture of Mr. Carlos Oliveira, we will be pleased to answer them. A part of that, as I already told you, you can revert back to me at any time. Here will you find my specific contact data. But there's no need to make any notes now in this presentation, as all the webinar will be available on the VentilAQUA website in the future for everybody. By the way, recently I have published a book, a compendium about the topic textile wastewater. And in case of interest, I can submit it to you for free of charge, as a PDF file. It comprises, on the one hand, the cleaning methods, recycling methods, on the other hand, proposals for the production integrated measures of wastewater minimization. Many thanks for your kind attention. My lecture lasted a little bit more than 30 minutes, sorry, but I think I was more able now to tell you the one or another thing a little bit more in detail. Many thanks for your attention, and now I would like to pass the word back to the moderator, Francisco. Thank you.
Thank you, Wölfgang, for your lovely lecture. It was very interesting and clarifying. I hope that you all enjoyed it too. As I told you before, any questions that you may have can be placed at the Q&A box at any time, so feel free to do it. We have already some questions in our queue line addressed to Wölfgang, but we will answer them after the second presentation. Next, we will be pleased to have the following lecture from Carlos Oliveira. We will address the topic of the available solutions for solving some of the problems that were raised and approached by Wölfgang. So Carlos, be my guest.
Good morning to you all. Thank you, Francisco. Thank you, Wölfgang. I hope I can give you a lecture at the same technical and scientific level of Wölfgang. It was very interesting, and I think it pointed out all the critical aspects we are discussing today. And we are really proud to have such a wide audience and diverse audience with whom we can share our knowledge and present them our technologies. So my lecture will be based on our technologies. I will first start by introducing a little bit VentilAQUA, and afterwards I will talk about all these technologies that can meet these new challenges and help all the textile industry around the world to reach that excellence level that Wölfgang told us about. VentilAQUA is a European company, an engineering company. We've been in the market for 23 years now, and we have based all our path, all our market on new technologies and knowledge development. So we are very focused on R&D, and we are very focused on delivering to the market new technologies, new solutions to face these new challenges of the modern world, and challenges which are bigger and more difficult every day. We have been working around the world, so today we can proudly announce more than 700 treatment plants around the world in all different sectors. We are present in more than 60 countries, so we cover all geographies, all languages, all cultures, and we can provide our systems and our technologies anywhere through a network, a huge network of representatives in a lot of countries that work with us and provide to our customers the full spectrum of our systems. Challenges in textile industry, that's what matters for us today. So we will be addressing these challenges in order to help you and support you in reducing costs, improve treatment and compliance, and increase the reuse of water. These, we believe, are the most important aspects any manufacturing manager looks at and worries about. So reducing costs basically means reducing chemicals usage, so reducing the logistics and the cost of chemicals, the risks of using chemicals. Then also reducing costs might come from reducing sludge production and using different technologies, as Wölfgang mentioned before. The traditional coagulation precipitation technologies can be replaced by other new technologies, and that will bring you a lower sludge production, so with all the advantage you can imagine from there. Also, reducing costs means reducing power consumption, and these new technologies also allow you to work with lower power consumptions. And space requirements. One of the big issues on textile industry in, well, I wouldn't say all the countries, but most of the countries and geographies is space requirements for these big plants. And obviously using these new technologies might help you reducing the size of the conventional or traditional way of treating water. Finally, reducing costs means also reducing fees. As you know, in a lot of countries, you have to pay fees to reject into the municipal sewer system or to reject into the environment. So if you reject less, if you reuse more, or if you reject with a lower contamination, you can pay lower fees. And by lowering your fees, you can pay back your investments. So this is a clever way of reducing costs and improving your efficiency. And talking about improving efficiency, it means also being compliant or improving your compliance obligations by reducing COD levels in your treated water, by reducing or eliminating color, by eliminating or reducing persistent COD or persistent contaminants, and by, for instance, reducing the tensioactive or surfactant presence in wastewaters, which is a common problem in the textile industry, as we heard from Wölfgang. So all these elements are also important and might be or not combined with the cost reduction. Finally, reusing water. Today, the textile industry faces these new demands, these new requirements, and we hear a lot about ZLD, so zero liquid discharge, and these all tendencies of reducing the water. Obviously, this is the way to go, but one needs to understand that most of existing conventional treatment plants don't reach a level that makes it easier or easy to reuse water, and adding on tertiary treatment systems with membranes and ultrafiltration and other elements causes a lot of mechanical stresses and consumes a lot of energy. So if we can reach a better quality of water by doing a proper pre-treatment, we can later on use these technologies, membrane, ultrafiltration, with an easier application, with lower power consumption, protecting our membranes, reducing odors, reducing foam, and protecting our filters. So all these technologies combined can allow you to better reuse your water. In VentilAQUA, we have a huge range of possible technologies. We deal with chemical technologies, we deal with biological systems, we deal with physical treatment. So all of them are applicable in a lot of different sectors, and even in the textile industry, of course. We also deal with the conventional treatment systems. But today we want to talk about, and we want to share with you these new technologies that can improve your efficiency and your performance in wastewater treatment. So basically, we will be dealing with electrocoagulation, dissolved ozone filtration, and perozonation. These are the new technologies that can help you reach your required treatment levels and reach your goals. So mentioning the previous presentation from Wölfgang and relating to that presentation, I want to give you a first introduction into these new electrocoagulation technology when faced with a conventional coagulation, flocculation, and precipitation. So as Wölfgang was presenting you, these effluent cleaning process, these separating processes require or are usually done through conventional coagulation, flocculation treatments. And one way to go, alternative way to go, is to apply one of these new technologies called electrocoagulation. I will explain you later the fundamentals of electrocoagulation, but right now just a comparison on technologies. So the great advantage of electrocoagulation when faced with conventional chemical treatment is the fact that we can have a higher degree of pretreatment with a lower reagent consumption, or no consumption at all, because in most cases we don't need to add any reagent to our electrocoagulation system. And from there we have lower power consumption, and one very important aspect, extremely low sludge production. The electrocoagulation system, or the electrocoagulation reaction, is usually a stoichiometric reaction, which means we don't produce extra sludge, we don't use extra chemicals, so the sludge production reduces dramatically when compared with chemical conventional treatment. And when we talk about textile industries, we always talk about huge flow rates, and for huge flow rates we have huge amounts of sludge. So if we can reduce sludge, we will reduce all the costs related to dealing with the sludge dewatering, sludge drying, and the logistics of shipping the dry sludge away for proper final treatment. So all this means a strong cost reduction on any textile company. Then we can apply these technologies into revamping or retrofitting existing plants, increasing compliance, increasing the plant capacities also, because we will increase the efficiency of the plant. We can remove those persistent contaminants that we mentioned before, like metals, colors, detergents, etc. What are the weaknesses or I would say difficulties around this technology, because not everything is gold. Obviously, we have a higher initial investment when compared with the conventional coagulation process, because the technology is more complex. But that initial capex is fastly recovered with a return on investment, short return on investment usually, and we have several examples on that. And we also have the electrode replacement instead of having chemicals. But we in VentilAQUA developed systems that allow you for a very fast, easy and friendly electrode replacement with a very low cost. I would say that the most inconvenience of all is basically the fear for the new and novel in industry. Obviously, electrocoagulation is a known technology for a lot of years, but as always, when you're dealing with new technologies, there's always the fear of moving first and having the troubles the others don't have. Then, still relating to Wölfgang's presentation, we have effluent cleaning, which is the next step. And in that step, we want to destroy substances. We want to disrupt substances, and we want to crack down resistant molecules and substances. So we have to use oxidative process. And on those, we can have either electrocoagulation, dissolved ozone flotation, or perozonation, or the combination of all these technologies altogether, which allows you to have a very strong oxidative and performant plant. So with all these technologies, we still comply with a lower reagent consumption as always. If we use ozone, we don't have any chemical reagent to add on. If we use electrocoagulation, we don't have any reagent to add on. We have lower power consumptions, lower sludge consumption. So basically, the advantages are the same in different steps of the process. That allows you to face these technologies, to face these solutions with a very optimistic point of view in terms of cost, and especially in terms of ROI, or capital return, which is one of the most important aspects that managers deal with. And obviously, when you compare these new systems with conventional systems for the same performance, your payback will be immediate. Obviously, if we compare with other conventional systems that don't get you to the same point, you can face differences in initial capital investment. But that's not a fair game, because with this, you'll be much further in terms of treatment. So allow me for a brief introduction on electrocoagulation technology. As a simple analysis on what is electrocoagulation, we can talk about a battery, a car battery. So in the car battery, you have an electrolyte solution, which is usually a aqueous acid solution that has conductivity, and you have electrodes from which generate electron current inside the battery and allow you to get current from the battery. So in this case, we are like using a battery, but on the reverse. So we have our electrolyte solution is our effluent, which has conductivity, and especially for textile industry, that conductivity is usually more than enough and sometimes quite high. So we can use it easily, and we will be supplying current to that battery instead of taking out current. But we supply very low voltage current. So we use between 2 to 4 or 5 volts, which is very low. And what will happen is that we will generate basically 3 main processes inside the battery. We will generate an electron current, so electrical current that will disrupt some links and some molecular connections. We will generate a ion current from the electrodes, giving to the system the metal ions like iron and aluminum that usually are introduced through liquid chemicals, and we will hydrolyze the water, generating very reactive agents like OH- and H+. So these reactive species will act as oxidative species into the molecules and disrupt these molecules. So the combination of these three phenomena will allow you to break down these molecules and have a coagulation process immediately without any chemical dosage, without pH modification, and with a very low sludge production, because the reaction will be basically stoichiometric. So this is a very strong chemical treatment process. I'm showing you a small video where a raw wastewater coming from a textile dyeing company and laundry will be treated on a lab scale electrocoagulation cell, as you see, and you'll notice that no chemicals are added into the process, and the color will be immediately removed, as well as all the solids. So as I told you, this system works with a very low current, so the power consumption is also very low, and they are usually dependent on conductivity on the effluent, which, as I told, in textile industry is not usually a big problem. So by pouring in a current, which depends, and we can come into different discussions about current density, about the size of electrodes, the number of electrodes, the type of electrodes. All these are tailor-made for your own system. So there is a standard technology, but there is not a standard plant for electrocoagulation. Every electrocoagulation plant should be designed and suited for a specific user, because we have to balance between the size of the plant, the requirements in terms of treatment, the cost of operation. So as you see from the video, we just dropped a few drops of flocculant to make the flocks bigger, and in less than 5 minutes we got an extremely clear vision of water with all color removal. So I repeat, we didn't add any chemicals to this water, and this was a raw wastewater from one of our plants running nowadays. So basically, what this technology allows you to do is to remove recalcitrant and difficult molecules, to remove color, to remove detergents and tensioactive, to improve reduction of COD and BOD, and to increase biodegradability of effluent before a downstream treatment. If you have biological treatment in your plant, and if you feed it with a easier substrate, obviously your plant will run better. So we can use electrocoagulation either as a first step or a tertiary treatment for a final process. So one of the innovations we brought into the electrocoagulation processes through our systems is the fact that we draw them on a friendly way, especially on the electrode aspect. So we draw and design our electrocoagulation cells in order to use very common and very easy to find electrodes. We don't bind our customers to the electrodes. They can make the electrodes themselves according to our drawings from common and standard steel sheets or aluminum sheets. So these cost, because they need to be replaced, because they are consumed along the process, this is a very low operating cost, because we don't have special electrodes as other competitors in the market. Okay, so this is basically one of the big advantages. Besides that, we provide our systems with an easy mechanical way to change electrodes. When you change electrodes, there is no risk at all, and the system doesn't stop, so you don't have any downtime when you change electrodes, because they are grouped by cells, by packs, and when you change a pack, you don't stop the system running. Okay, so and we have also a device that allows us to clean continuously the electrodes along its operation, avoiding any passivation or blockage problem. As you see on our green tag, usual cost for an electrocoagulation system, or OPEX costs, including all costs, meaning electricity, electrode cost, operation, usually goes below 0.25 euro per cubic meter, which should be around $0.20 per cubic meter. So this is a very low cost and uncomparable with any conventional chemical treatment. Let me show you some examples of existing treatment plants that we made with electrocoagulation. So in these systems, as you see, very compact and can be installed outdoor, indoor, it doesn't matter. We can use them for grease removal or fats removal, tensioactive removal, color removal, COD removal in terms of direct reject, detergent and tensioactive or surfactants removal. We can go below 2 ppm on detergents without any filtration, without any activated carbon, without any membrane after the electrocoagulation cell. We just need to separate the water from the sludge with a DAF system or a settler, and we reach those treatment levels. We also have for hard molecules removal or disruption to make it easier for the downstream treatment to deal with those molecules. Electrocoagulation is very powerful on emulsion breakdown, so any emulsion will be breakdown and can be precipitated after an electrocoagulation process. So these are some examples of our electrocoagulation cells. They can be combined by cells, different sizes, different layouts. We can use them inside maritime standard containers, or we can have a tailor-made operation. So as you see, everything is quite friendly and quite easy to work with and to deal with. The second technology, or the second chemical approach I want to mention, is ozone, either through dissolved ozone flotation process or perozonation, meaning saturation with ozone. VentilAQUA was the first company in the world, as we know, to have marketed ready-to-run dissolved ozone flotation units. Okay, this means on a flotation process, we replace air by ozone, and we reach a different level of treatment, because besides separating the sludge, that's what a DAF system does, we also oxidize the effluent very strongly through ozone presence, and that allows us to have a much higher efficiency in the process. Okay, so these are processes that allow you to go to a very much further in terms of efficiency on removing these contaminants, on removing color, on oxidizing difficult molecules. Also, you can use them as a final step in your plant, and you'll get a disinfection. So because ozone will kill all bacteria and viruses in your water, and every effluent is contaminated with microbiology activity. So also allows you to have a disinfected water at the end. I mean, it's not the first priority you might have in a textile operation, but it also helps. So, and basically color removal is also one of the key aspects. So using dissolved ozone allows you to have a very simple and power process with very low OPEX, because you only have electrical consumption and you generate ozone from air or from oxygen or concentrated oxygen flow. The capital investment is not that high, although people think it is, because today ozone generators and ozone control devices are becoming quite affordable in the market. It allows you to have a very compact, so with very low footprint plant regarding flow rates, because the oxidative power is so strong that you don't need large residence times or retention times. You have no negative effects on downstream biological treatments, which is very important for a first step treatment or eventually a middle treatment in between an existing plant. Only requires to be attentive to eventual ozone leakages. So the systems are equipped with all protection devices, with ozone detectors. We have no history or no records of any problems with ozone leakage, although also ozone is very unstable. So from the moment it escapes, it will disappear very fast. It allows you or avoids you to have any risk on excess ozone in the area. Just showing you some examples of very, very powerful treatment plants that we have running, combining electrocoagulation and ozone all together to destroy real hard effluents, molecules, and get real hard effluents to be rejected below the accepted limits on municipal sewage networks. And referring to textile manufacturing, we have the experience of eliminating or reducing PVA concentrations through electrocoagulation and ozone altogether with much higher efficiencies than the conventional treatment, and reaching a very much further in terms of reject limits with a much lower operating cost. So that allows us to reach a level which was not reached before, and in some cases reject fees are paid according to the organic load you have in your effluent, and if you lower that load, obviously you will lower your fees and you'll get a return on investment based on that. So again, ozone, dissolved ozone, or peroxonation can be used either as a first step or a tertiary treatment. They are easily added on existing plants, so retrofitting or revamping existing plants, and they will contribute for what are the main problems on textile industry. So color removal, detergents removal, hard COD removal, or hard molecules disruption for a later removal. A short textile portfolio on some of our existing plants. Dyeing, so as you see, red is a common color around the textile industry. So we have either these big plants dealing with big dyeing, or we also deal with textile printing and textile serigraphics on smaller scale plants, because flow rates are smaller and we can have these same technologies fitted in a more compact displays. I'd like to draw your attention into the left side pictures, because I like that very much, and I usually show them in my presentations. And on top left, you can see the before and the after. So, I mean, the fact that we can contribute to improve environmental footprint, the fact that we can share our knowledge and our technology with our customers and help them have a better image, have a better impact in the community, and helping also to teach their staff, their employees, that it is important to protect the natural resources. It's also a key factor for our success, and we worry a lot on contributing to that evolution. So these pictures are really important to us, and they were to our customer in this situation, because the existing status was really bad, and then they managed to evolve to a new very positive situation in terms of environmental protection. So a few more pictures on other plants that we have, just for you to have an idea of our capabilities. Also in terms of our compacted device, so we can have either settlers, DAF systems, DOF systems, electrocoagulation, perozonation. So all these systems together, either on small compact displays or big, huge plants, we can make them in all these different shapes and forms and sizes. As I told you, basically the technology might be standard, but the plants are tailor-made for each company. So I'm coming to the end of my presentation. I hope and I expect I could meet your expectations, and that it was elucidative for you. And obviously, as Wolfgang said, we are available for you right after my lectures for any questions. I know that a lot of questions have been already shared and published. So thank you very much for your attention. And I'll be passing my word to Francisco to moderate this Q&A phase now. Thank you.
Carlos, thank you very much for your lecture. It was also super interesting, very complete and enlightening. So, as referred before, we will now have the chance to answer to some of your questions and doubts. We have a huge participation from our audience, which is good. You have been very active and placed a lot of questions and doubts. So I think we can start now. First, maybe we can consider the first question to Wölfgang. So Rama is asking about low bioeliminable. Does it refer to hard COD difficult to biodegrade? And also is looking for you to explain again your slide number 22 about economy versus flexibility.
Okay. I will open my presentation. Give me a second, please. Is it visible? Okay, you can see my presentation. And the slide number, please tell me the number again.
22.
22.
Yeah.
Okay, the question was, I should explain more the economy and the flexibility.
Yes, I suppose so. Yes.
All right.
Yeah.
Let's first see the economy. The economy means at the same time efficiency. And efficiency does not mean only the effect, but also the costs you have to invest. Actually, in the order from the top to the bottom, there's increasing the efficiency, the effect, and the saving of money. In case of the first one, for instance, recycling of wastewater mix, this is rather expensive, and it is not too effective. It's a matter of fact that the lower is the volume of the liquor, the more efficient is your process of cleaning. The higher is the volume of liquor and the lower the concentration of ingredients, respectively, the lower efficient is your system. Yeah. So actually, if you are looking for methods to apply, you should avoid this one, but at least prefer the partial flow treatment, which is already more efficient and also less cost effective. And if possible, even you should prefer the last two processes. I will explain now a little bit more, which don't need any cleaning method at all. In case of a reuse of contaminated rinsing liquors, you don't need to clean something, just to collect the last rinsing liquors, for instance, of a reactive dyeing, the last 2 baths of rinsing, or in case of bleaching, the last bleaching baths. You can collect them, and then you can reuse them for at least first rinsing, if not for dyeing or bleaching itself. On the other hand, in this case, of course, you are less flexible and you have to invest more expenditure for measuring, for controlling the system. So this is more sophisticated, for instance, than this one, but it's more efficient. The reuse of treating liquors, by the way, is even more useful. You don't need any separate equipment to collect the water, but you can leave the liquor in the treating device itself, in the dyeing machine, and you can reuse this bath. On the other hand, you have much sophistication here, because you have to control, to measure the composition of this bath, and you have to calculate the refreshment additions, and so on and so on. So from the top to the bottom, it is getting less, it is getting more economic, but also more sophisticated. You need much more know-how here than there. I hope this is answering the second question. Concerning the first question, I would like to ask you to repeat it, because you spoke about bad biodegradability. Can you repeat, please, Francisco? What was it?
Yeah, he's asking about when you refer to hard COD or low bioeliminable COD, yes. If it is hard COD for you, it's difficult to biodegrade.
Yes, of course. I shall explain why. Actually, there are substances which are, for instance, polyvinyl alcohol is a common size. Polyvinyl alcohol actually cannot be decomposed by the aerobic biology-based municipal wastewater plant at all. It cannot be reduced, it cannot be removed, it cannot be cracked. The aerobic biology is too weak for that. In this case, for instance, you have to crack it, for instance, by ozonization, and as soon as the molecules are cracked, then they are accessible to the aerobic biological treatment.
Okay.
If it's answering that. So you have 2 different kinds of substances. You have substances which are well bioeliminable by aerobic treatment, and those which are not well bioeliminable. And actually, there are a lot of dyeing auxiliaries and also of preparations for the textile, for instance, the add-ons, the oil on the knitted goods, which are very difficult to be eliminated, but at the end they need to be eliminated, because the municipal wastewater plants are forced not to exceed a limit of COD value in their output. Yeah, and therefore there is often the necessity of the company. They are forced even by the community to reduce the bad bioeliminable components. If they cannot reduce them in their production because they are crucial, they have to apply any system, for instance, flocculation or ozonization, in order to make them better biodegradable. We have got the problem recently, Carlos is remembering it, with polyvinyl alcohol. The company was under pressure. They have desized polyvinyl alcohol, and the biological wastewater treatment plant was not able to decompose it, and therefore they have been forced to introduce the ozonization in order to make these persistent these recalcitrant substances as polyvinyl alcohol to be better bioeliminable. Thank you.
Okay, maybe we can consider another question for you from Mr. Pagado. He's asking by new dyes, if you mean natural dyes or new chemistry dyes.
The new dyes. I make an example. And these new dyes are mainly concerning actually the reactive dyes. Mr. Abigado, I know him very well, and I welcome him to attend. The most important dyes at all nowadays for cellulosic dyeing, for cotton dyeing, are the reactive dyes. And the reactive dyes are the dyes which are the most serious ones for dyeing, for effluent, because their yield, their exhaustion is the lowest. And the concentration of them in the effluent is the highest. And they are not accessible to the aerobic biology. Now we have one case of recalcitrant substances which are not eliminable, and therefore there is a demand for the dye houses either to clean the water, to remove these dyes by flocculation, for instance, or to use new dyes, better dyes, improved dyes, reactive dyes, which are less, not which are better bioeliminable. Reactive dyes are never bioeliminable, but which are less impacting the effluent because the yield is much better. And I can give you examples from that. Particularly the companies, the dye stuff suppliers Huntsman, Dystar, and Sumitomo Japan are offering these dyes. For instance, there is the range of bifunctional reactive dyes like Novachrome C from Huntsman or Sumifix Supra from Sumitomo, which have a high degree of fixation, and therefore the residual dye stuff in the effluent is no longer 30%, but only 10% or even only 5%. Though you can reduce considerably by highly reactive dyes, by bifunctional dyes, you can reduce considerably the concentration of reactive dyes hydrolysate in the effluent. There are also other systems now developed, for instance, the Cardira system from reactive system from Dystar or the Novachrome LS system, which require only low concentration of salt, because the salt concentration usually is 50 gram per liter. For these dyes, you need only 10 gram per liter. So also you cannot, by using new reactive dyes, you cannot only reduce the contamination of effluent by dye stuff, but also you can reduce the salt considerably. Okay, Mr. Abigado has asked me, but at any time, if you are looking for more details about better dyes in order to reduce the contamination of the effluent by either dyes or by salt or by alkali even, or reducing the temperature of dyeing or the temperature of soaping, saving energy and other costs, you can approach me and I can mediate you with the best suited dye stuff for every purpose. I'm an experienced dyeing engineer for 30 years already, and therefore more or less I know all the available best state-of-art products available. I can inform you about. Okay, thank you.
Okay, thank you. Maybe now a question to Carlos. Aviraj is asking, in electrocoagulation, which method do we use if we apply current on monopolarizer or bipolarizer methods?
We cannot hear.
I forgot my mic. Okay, sorry, I forgot my microphone. So as I was saying, our systems are designed in order to change polarity a long time, so that the sacrificial anode, which is degraded and consumed a long time, will be equal along all the electrodes present in the cell. I believe that was the meaning of the question. So that allows us to consume all electrodes the same way a long time, and we avoid having anodes, small anodes and big cathodes. So every electrode will be either anode and cathode in some moment. We can set up that polarity change a long time, and it's automatic. So we just set up in our PLC, and from every 5 minutes, every hour, doesn't matter, every 2 hours, they will change from anode to cathode, and the consumption of electrode will be similar to all electrodes. So that's one way of improving the efficiency and improving also the lifetime of the electrodes in the electrocoagulation cell. I hope this was the meaning of the question. Francisco.
Okay, thank you. Another question from Lucy. Lucy placed a lot of questions. I don't know if you will be able to answer to all of them, but maybe you can reach us after the webinar. But some of the questions are if we have problems with iron in wastewater after the EC process, and what pH is used during the EC process. So what if the water is alkaline or salty? For you, Carlos.
Okay, thank you. So regarding pH, obviously we can optimize the operation of electrocoagulation process by setting up the ideal pH. But in other cases, we don't even need to touch pH, because as we are performing a water hydrolysis, we are obviously generating OH- and H+. So the species that are important for pH regulations are already present, and they kind of self-regulate. But anyway, in some cases, we need to address that problem and either add an alkali or an acidic reagent to bring the effluent to the ideal pH for reaction. Regarding iron or even aluminum, depending on the electrodes we are using, obviously there is always some remaining metal dissolved in water at the end of the process, and we can eliminate it either through adding an oxidative reagent or eventually inside the cell itself by oxidizing this metal and bringing it to a precipitate phase and having it in the sludges. For every electrocoagulation process, we need a downstream sludge separation device, either a settler or a flotation unit. So those sludges will be separated from the mainstream, and the water will flow to the next treatment step, if there's any, and the sludge will be removed from the process. So those sludges might contain some iron or some aluminum, but again, as reaction is basically next to stoichiometric, those amounts are really small and doesn't cause any kind of trouble for those sludges to be handled later. Francisco.
Sorry, I also, thank you, Carlos. I also would like to contribute something from dyeing point of view to this question. Actually, iron is not a problem at all for any wastewater if it's discharged directly or indirectly, because it's not regulated. There's no limit, it's not toxic at all. But it is a huge matter in case of you want to reuse the water for dyeing or for finishing. Iron is the most serious impurity in water at all, for instance, for dyeing purposes. The most serious one. There's a limit of 0.1 ppm of iron, which is not permitted to be exceeded. 0.1 ppm is the maximum iron permitted for reuse for finishing processes, particularly dyeing processes. This means, of course, if you want to reuse the water for finishing, then of course you have to add after the electrocoagulation process another method like reverse osmosis, electrodialysis in this case. But it is necessary generally if you want to reuse the water for finishing.
Sure.
That's it. Okay, thank you.
Yeah, thank you.
Maybe,
yes,
Wölfgang.
I mean,
Sorry. Go ahead, Carl.
Yeah, the idea of electrocoagulation is to have a better pretreatment for downstream tertiary treatment. So obviously, after any electrocoagulation or other kind of treatment, if you want to reuse water, it doesn't eliminate the need for filtration, ultrafiltration, or a reverse osmosis, depending on the level of reuse you want to reach. So I don't want to leave the wrong idea that electrocoagulation will replace all the other methods. It's a complementary method. It eventually replaces conventional chemical treatment, not the tertiary operations with membranes or whatever process we have. Okay.
I would like to pick up this question, also giving you a general information about heavy metal ions in the effluent. As you know, in dye houses, or yes, mainly the heavy metal ions are not free as ions, but they are complex bonded within the heavy metal in the metal complex dyes. The heavy metal ions, to be removed, it would be difficult. You would need a reverse osmosis process usually if the oxidation itself is not strong enough. The reduction at the cathode to transfer them to sedimentable solid heavy metal. But in case of dye houses, usually chrome, cobalt, copper is usually complex bonded, and this can be easily removed by electrocoagulation due to the matter of fact that these dyes are precipitated, and hence the heavy metal is removed. Yes. Nowadays, there are only very few cases where free heavy metal ions are present. One case are special antimony treatments for finishing, or is even the antimony which is coming from the polyester fiber. Actually, the polyester fiber is containing antimony as catalyst for production, and this antimony is leaving the fiber during dyeing and also affecting the effluent. And if you would like to remove this antimony, actually, this is not regulated usually. Antimony is not regulated, but if you have to remove it, in this case, a reverse osmosis, either a reverse osmosis or the cathodic reduction might be necessary. Question to Carlos, do you think when we speak of antimony or when you speak of chrome for, let's say, free chrome ions for, let's say, leather industry, is the cathodic reduction strong enough to convert the heavy metal ions to free solid heavy metal, which is sedimenting? Is it strong enough?
Yes, it is, and we have that experience with leather industry, okay, and with chrome, because in the electrocoagulation you have a oxidation and a reduction reaction, so all together. So you can actually have a chromium 6 to chromium 3 conversion, and then you can precipitate chromium that will come out in the sludge as a precipitate, obviously, but the water will be absolutely clear from that. We use this a lot on the metalworking industry, for instance, on the automotive and the car industry. This is a common contaminant, much higher in concentration than in the textile industry, and we have that experience. So we have real plants running on chrome elimination and other metals elimination through electrocoagulation, and especially, and it's very important to point out, we don't need any, as you all know, I presume, when you are precipitating metals, you need to balance between your amount of metal concentration and the pH you need to reach for metal precipitation, so that you can combine the metal ion with the OH. In this case, as you are hydrolyzing water, you are already generating the radicals and the OH and H+. So you don't need to add any alkali reagent to raise pH. You can precipitate metals at a low pH without any difficulty, and you don't generate more sludge, because when you are adding lime or any alkali reagent, you are always adding in excess to reach the right reaction level, and then all these elements will react between themselves, and you have sludge that comes from the contaminant itself that you want to remove, but you also have sludge produced by other elements. In this case, you only have the sludge coming from the contaminants because you are not adding anything at all. So it's much better to use an electrocoagulation process for metal removal than any other method, to be honest.
Thank you. Mm-hmm.
Okay, for you again, Wolfgang. Suzanne is asking if in modern dyes, as you said, more efficient and environmental friendly, she's asking if she still needs a treatment plant when she's using these modern dyes.
Yes, she will. By modern dyes, I have spoken about reactive dyeing, might permit you to save energy, might permit you to reduce the concentration of dyes in the effluent. But even the modern dyes, let's stay at cellulosic dye stuffs. Let's stay at reactive dye stuffs. Even the very, very best reactive dye stuffs in terms of environment are not biodegradable. You understand? They are not biodegradable. There are some dyes like dispersed dyes for polyester, wet dyes for cellulosic, all the dyes which are not water soluble, they are biodegradable. But all the water soluble dyes like reactive dyes, direct dyes, acid dyes, metal complex dyes, or basic dyes for polyacrylic dyeing, nearly none of them is biodegradable sufficiently. When I say not biodegradable, it might be biodegradable by 50–60%, but actually the demand is more than 80%. And therefore, even the best dyes you have, if you have not an optimum yield of dyeing, if you have too much dye stuff in the effluent, and if the color at the end of your effluent or of the river at the end is affected, then you are forced to apply any system like flocculation to remove this color. Yeah. So generally, once again, the new dyes are helping you to reduce the contamination of the liquor. For instance, by 300% less in case of better exhaustible reactive dyes. But the residual dyes which are there, maybe it's enough, then you have no longer a problem with the color in the effluent because the limit is no longer exceeded. But if the limit is still exceeded, then you need a treatment, because even the best dyes in the world, the most modern dyes, they are not biodegradable. The water soluble dyes. This rule you can use generally, by the way. More or less. Okay?
Okay, thank you. For you, Carlos, Rema is asking, what do you do with the H2 that is generated as a byproduct in the electrocoagulation process?
Okay, this is a interesting question and quite a common question. People are afraid of hydrogen production. I would say, as a first approach, that unfortunately is not that much. Otherwise, we would become rich by producing hydrogen so easily. Hydrogen is very unstable, so yes, it produces some hydrogen from the hydrolysis reaction, but as soon as hydrogen reaches the surface of the water, it's so unstable that it doesn't stay long. But the rates of hydrogen formation are very low and the concentrations are very low. Besides, we are talking about wastewater treatment plants, so we are talking about systems that are installed in wide areas or open air or big buildings. So there is not a concentration anyway in some cases where the internal area is more critical. We have dedicated ventilation systems, so we cover our electrocoagulation system with aspirated hoppers, and we can throw out that, I would say, air mixed with some tiny concentration of hydrogen outside, but it's not explosive, so it doesn't generate any risk.
Okay, thank you.
Sorry, Francisco. I would like to come. I would like to come back to the question of Susan previously because of DICE, because there is one thing which is very crucial to know, and now I would like to emphasize that. You have heard, soluble dyes are not biodegradable at all. But what you can do, except a wastewater treatment problem, you can do something. You have just to increase the yield to an optimum. You have to try to achieve 100% exhaustion. Then there is no longer any dye stuff left in the dye bus. How to do that? I have practical experience with that. In case of wool dyeing or polyamide dyeing, where acid dyes are used, for instance, just increase the acidic pH at the end of the dyeing. Then you will come from 90% exhaustion to 99% exhaustion, just by increasing the acid concentration. Even, by the way, in this case, I have examples to reduce the chrome and cobalt in the effluent, just by increasing, by lowering the pH of acid dyes or metal complex dyes, because in this case they exhaust completely and there is no longer left any complex bonded chrome or cobalt in the effluent. In case of cotton dyeing, for example, reactive dyeing, the best choice is to use the modern types of dyes like Novachrome LS and so on. Novachrome C and Sumifix Supra, which permit you a better exhaustion, but you will never get a better one than 90%, I guess. In case of direct dyes, you can only increase the concentration. You can only increase the concentration of salt, acer, or you can use a precautionization of your fiber, which makes your fiber cationic, hence the yield of direct dyeing is by 100%, but you have some problems, maybe sometimes in this case with fastness, with levelness. And therefore, the cationization, despite of increasing the yield of dyeing, of direct and reactive dyeing by far, is not generally recommended because it has some other threats and dangers in it. In case of polyester dyeing, in case of wet dyeing, there is no problem at all with residual dye stuffs. On the one hand, they are no water soluble and therefore they are eliminated completely in the biological wastewater plant. On the other hand, the yield of dispersant wet dyeing is nearly 100%, so nearly nothing left in the effluent. In case of acrylic dyeing, also the acrylic dyes are soluble, they are cationic ones, they are not bio-eliminable, but even the acrylic dyeing is nearly by 100%. So last but not least, the only problems with dyes we have got in the main problems with dyes we have got in reactive dyeing with the worst yield. We can solve this problem by new dyes. And in case of acid and metal complex dyes for wool and polyamide, where we can solve the problem just by lowering the pH at the end of the dyeing process. Before you think generally, before you think about a method of cleaning, sorry, Carlos, because this is your daily money. And
no.
But before you think about cleaning methods, first, and this I already emphasized during my lecture, you should think about the production integrated methods of reduction of rate. What I can do in the production to lower the concentration of my ingredient in the effluent. And that's something I'm especially an expert for that, to help you, because I'm a textile engineer and textile chemist, and This is my job I am already doing for 30 years now, to help my customers to minimize their pollution, their impact of wastewater. Thank you.
Sure.
Okay, thank you. Maybe another question to you, Carlos. Victor is placing questions slightly different, but I think also very interesting. He's saying that textile industry has some similarities with pulp and paper industry. He is asking if you have any know-how about color removal in pulp and paper process effluent.
Okay, yeah. Well, actually, yes. We have done some work in the pulp and paper, namely on AOX reduction with very important and successful results, and on color removal also in the same process, meaning that when we put these waters or these effluents through the system, besides having AOX reduction, we also have some color reduction, although it might depend on the process and on the company whether the strongest color comes from that stream or other streams. But yes, we have done some experiments with electrocoagulation and electrooxidation on the pulp and paper industry. Results are quite interesting and promising. It's a novel approach to that industry also. And I mean, we are more than open to discuss this subject if anyone from that area approaches us, obviously.
My contribution to that, thank you, Carlos. Actually, the composition of the water of the pulp and paper industry and the cellulosic dyeing industry is more or less identical. The dyes, for instance, used for paper, they are identical. They are direct dyes which are identical with those used for cotton dyeing.
Okay.
And the composition is quite close to. Even the bleaching is nearly the same. Peroxide bleaching is used in both cases. The impurities of the native material is nearly the same. The after fixing agents for clearing, for improving the fastness of the paper and the cotton, the direct dyings is the same. So there is no industry which is more similar to each other in terms of effluent than the pulp paper industry on the one hand, and the dye houses, particularly the dye houses using direct dyes, cellulosic direct dyes on the other hand.
So this was an interesting question then.
Okay, another question from Susanna to you, Carlos. She's asking if she can improve the biological treatment plants with the EC technology, with electrocoagulation.
Yes, obviously. By putting an EC process before, we can increase biodegradability of molecules, so of contaminants, and thus increase the efficiency of the biological process downstream. So we will feed our biological treatment with an easier substrate than previously, and the bioactivity will be improved, obviously. We can also have the electrocoagulation as a secondary step, so after the biological treatment, to increase the oxidation of some elements that might go through the biological treatment and still be present in the effluent. One important thing is that having an electrocoagulation process does not negatively affect any biological treatment downstream, and which I think that's the most important thing to notice and to point out, because some strong oxidation processes sometimes affect downstream systems, which is not the case here.
Okay.
I would like to add something. In this case, again from textile chemical point of view, I already mentioned in my lecture that more than 50% of the COD value in the effluent of textile dye houses, textile finishing companies, is resulting from the preparations and the sizes. The preparations of the yarn and knit goods, which is mainly mineral oil, and the sizes from the woven fabrics. And this is the main contribution of COD. On the other hand, just these components are not biodegradable. These components are not biodegradable. Okay, sizes in case of starch size, yes. In case of synthetic sizes, no. Polyvinyl alcohol, polyalcoholate is not biodegradable. And in these cases, an ozonization or electrocoagulation in order to crack these components, Carlos has used any other term for cracking, I cannot remember.
Disrupting.
Disrupting, exactly. To disrupt these components in order to make them accessible for an aerobic biological elimination is very interesting and very important.
Absolutely, absolutely.
And even if nowadays the laws are not so restrictive yet, and even if nowadays 90% of the companies don't need any treatment of their effluent yet, it might become more serious in the future, because the laws and the limit values are getting more and more restrictive.
Yeah, you're right.
The necessity for a pre-treatment of wastewater prior to the municipal wastewater plant is becoming more and more important in the future.
Yeah, yeah.
Okay, thank you. Well, we are already very advanced in time. Maybe one or two questions more, and then we'll finish. For you, Carlos, Lucy is asking, what is your opinion about combining ozone and electrocoagulation in the same reactor, like a ozone assist VC?
Okay, great question. Thank you. Extremely positive. We have that experience also by bubbling or injecting ozone into electrocoagulation cells. Obviously, we improve the efficiency on oxidation. We improve the concentration of active species into the water. So the powerful outcome is noticeable. And by the way, some of the two examples I showed earlier with the two difficult industries, they are actually combining electrocoagulation and oxidation and ozone processes to remove, for instance, formaldehyde and other cyclic and polycyclic molecules, very hard to remove. So yes, mixing or injecting ozone into electrocoagulation cells is a step forward in increasing oxidative approach. Obviously, we don't need that every time, so we need to understand what are the purposes and the levels we want to reach in terms of contamination reduction.
Okay, just one more, also interesting from Lucy. If she's asking if we have experience of using plasma for wastewater.
Plasma?
Plasma, yes.
To be honest, once I heard from that, I cannot remember where, but I'm watching all the new developments which are published in internet and in the newspapers. And actually, I have not found that technology yet for wastewater treatment, which is realized in practice. Maybe it's still in state of science. On the other hand, as far as I know, plasma is only working in air and not in water. Plasma is generating positively and negatively charged radicals, ions, intensely. And as much as I know about plasma, and I'm cooperating with a plasma company named GRIMP, they have a device for textile pretreatment, I told you before. As far as I know about plasma, it's only useful in air, but not in water medium, not in aqueous medium.
Allow me to add something, because actually we have that experience. I mean, it's funny Lucy put this question, because actually 80 years ago we led an international consortium on a project called Water Plasma, and we were actually removing recalcitrant molecules with plasma in water.
Really?
So,
oh,
sorry to correct you.
All right. I'd like to learn it.
You are right. You are right when you say there is no available commercial system in the market, because there isn't, and we know why. Because we had a lot of troubles trying to put plasma running in water, and basically all these problems are hydraulic problems, not energy problems. Only hydraulic problems, because you need to guarantee a very thin water layer, and that's the most difficult thing to achieve. But we have that experience. The project was called Water Plasma. We were removing pharmaceutical components from water with plasma. It was extremely effective, I have to say. At the end, it comes to a combination of ozone and electrical discharge into the molecules, because the plasma will generate ozone from the oxygen content, which is also very interesting. But then due to the hydraulic difficulties of guaranteeing or ensuring a proper electrical corona stable to produce the plasma, I think things were a little bit put on hold, and I'm not sure if it is a real promising technology due to the costs it will incorporate in terms of hydraulic layout and hydraulic setup. But yes, it's interesting, because it was a very interesting project we led. It was a project with 7 countries and supported by the European Commission 8 years ago.
Okay, thank you. Well, I think we can conclude this webinar now. We have been live for about 2 hours, so much more time than we were expecting at the beginning. The majority of the questions have been answered. We still have some questions left, but maybe all the people that have any additional questions can reach us after, or eventually we can get in touch with you. I hope that everyone have enjoyed the webinar. But before ending, I think that both Carlos and Wölfgang would like to say a few words. So please, Wölfgang, before we leave.
Yeah, thank you, Francisco. Ladies and gentlemen, many thanks once again for your kind attention. It was a very interesting seminar for me. The questions have been very competent and relevant, actually. Actually, I expected some of those questions, and therefore I have prepared me particularly, because I usually know the questions which are the most ones, the main ones occurring from textile companies. As I already told you, you can approach me, and as well you can approach Carlos at any time. If there are some questions or problems occurring, we can talk more about every detail. And I hope we can find a solution in as good as every case, either by a proper method for cleaning, recycling, or by avoiding of effluent flow. And by the way, I have mentioned that I have published a book about textile wastewater cleaning, a compendium. Somehow it's bilingual, it's both in German and English language. And you can ask me to send it to you, but you can also check my website, www.höhn/textile.de. You can download it for free from this website again. Also, goodbye, take care, and keep healthy. Many thanks. Bye-bye.
Okay, so my part now, I want to thank everyone who attended this webinar. It was an honor to be here talking with you, and mostly being able to perform what is one of the goals of VentilAQUA, sharing our knowledge. I think knowledge was quite evident in the presentation of Wölfgang Höhn and his wide experience in the textile industry and deep knowledge on all aspects related to the textile industry. We humbly shared our knowledge on the technologies that we've been developing to address those challenges and the new challenges of industry. We keep obviously totally available for any contact you might want to start. As I told you before, we are present around the world, so we can help you anywhere, anytime, and we'll be more than glad and proud to contribute for a better future. Thank you, everyone.
Okay, thank you. Thank you, Carlos, and thank you, Wolfgang. So it's up to me to officially close this event. Feel free to contact us for anything you may need from VentilAQUA. We'll make all these webinar, the video, and all the presentations available for you in the next days. You will receive an email with a link that will allow you to download all this documentation. Also, in any case, of course, you can reach us at any time and through our website. So thank you all. Thank you for being here and hope to see you soon. Okay? Bye-bye. Thank you.